Have you ever wondered how literally billions or even trillions of tiny transistors on a microchip get organized? Well, it's definitely not magic. It's one of the most critical, most complex steps in all of engineering, and it's called placement. So let's dive in and see how we build a perfectly optimized silicon city, right from the ground up.
So you start with this. It looks like chaos, right? It's basically a giant tangled web of connections called a netlist. And the mission, should you choose to accept it, is to take this digital spaghetti and create a perfectly ordered, incredibly high-performance layout on a tiny piece of silicon. The real question is, how on earth do you even begin to solve a puzzle with a billion pieces? Well, you do it with a tool that acts like a master city planner. But here's the catch. This planner has to achieve three completely conflicting goals, all at the same time. It's this incredible balancing act where making one thing better can easily make something else way, way worse. First up, goal number one, you absolutely cannot have traffic jams. In chip design, we call this congestion. We have to place all of our components, our buildings, in just the right spots so that there are enough routing tracks, enough roads for all the data to travel between them without getting stuck in gridlock. Second, short commutes. Nobody likes a long commute, right? This is our timing goal. Any components that need to talk to each other a lot have to be placed as close together as possible. Why? Because the shorter the wire, the faster the signal zips across, and the faster the entire chip performs.
And finally, goal number three, you have to manage urban sprawl. This is all about controlling the chip's area and its power consumption. You want a small, dense city because it's cheaper to build and it's way more energy efficient. You just can't let your design get all bloated and power hungry. And this image just nails the core challenge. You see, you can't just pick one goal to be good at. If you cram everything super close together to make your timing amazing, you'll create these massive traffic jams, terrible congestion. But if you spread everything out to fix the congestion, now your commutes get longer and your timing tanks. It's a constant, delicate trade-off. So, the big question is, how does this digital city planner actually solve this impossible puzzle? Well, it doesn't guess. It follows a very precise, automated master plan, a step-by-step blueprint for building the entire city. And here's that blueprint, the pipeline. It starts with a rough sketch of the city. That's global placement. Then it snaps every single building perfectly onto the grid. That's legalization. After that, it reinforces the city's infrastructure with high fan-out net synthesis. Then it does a bunch of optimizations before finally cleaning up all the wiring for the city's test structures. Now, check this out, because this is where the magic really starts to happen. On the left, in global placement, the tool has figured out the best general neighborhoods for all the cells. It's okay if they overlap a little bit. But then on the right, it performs legalization and bam! Every single cell is snapped perfectly onto the manufacturing grid, creating this beautiful, non-overlapping final layout. But hold on, this city isn't just built at random. Just like a real city, our Silicon City has a very strict set of zoning laws. These are rules that tell the planner exactly where it can and cannot build certain things. And following these rules is absolutely crucial. These rules often come in the form of placement blockages, which are basically no-build zones. A hard blockage, for example, is like a protected park. You are absolutely not allowed to place standard cells there, period. A soft blockage might be a bit more lenient. Maybe it only allows essential utility cells like buffers. And then a partial blockage is like a density limit, telling a neighborhood it can only be, say, 50% developed. Then you have something called bounds, which are honestly best described as special economic zones. These are rules that force a whole group of related components to stay together inside a specific region. It's like telling all the big banks they have to build their headquarters in the downtown financial district just to make sure they can all communicate with each other as efficiently as possible. Okay, so you've got a great plan, you've got your zoning laws, but we're still building a megacity with billions and billions of components. And just like in the real world, when you operate at that scale, you're going to run into some massive infrastructure problems that need some seriously clever upgrades. So here's a classic problem. Imagine one giant water tower trying to supply water to thousands and thousands of homes all at once. The water pressure at the furthest homes would be terrible, right? Well, that's exactly what a high fan-out net is on a chip. The solution? You build smaller, local water towers along the way. We call them buffers, to break up the load and boost the signal, ensuring everyone gets what they need. And wow, just look at this before and after. On the left, that mess is the city's essential maintenance and testing network. We call it a scan chain, and it's crisscrossing the entire design. It's a total rat's nest.
After placement, the tool is smart enough to reorder everything based on where the cells actually ended up, untangling all those wires and massively reducing congestion. It's just beautiful.
So after all of this mind-bogglingly complex automation, the tool gets the design about, let's say, 99% of the way to the finish line. It's done an incredible job, but that last, stubborn, really tough 1%, that requires a final inspection. That's where the human touch comes in. And at this stage, we're usually left fighting two big villains. First, timing violations, where critical signals just aren't arriving on time. And second, congestion, these stubborn digital traffic jams in certain neighborhoods that the automated tool just couldn't figure out how to solve on its own.
And this right here, this is what that reality check looks like. That bright red path snaking through the chip highlights a critical timing failure. A signal is taking way too long to get from point A to point B, and if an engineer can't fix this, the entire chip could fail to run at its target speed. And to hunt down those traffic jams, engineers use amazing visualizations like this one. It's a congestion heat map of the chip. The blue areas are totally fine, plenty of room. But the red and yellow spots, those are digital hotspots, places where the demand for wiring is way higher than the available space. The engineer has to go in, sometimes manually, and figure out a way to cool things down. So what can an engineer actually do? Well, they've got a whole arsenal of techniques. They can make certain cells bigger and stronger to push the signal harder. They can swap in faster, higher performance versions of cells. They can strategically add those little buffers we talked about to break up long wires. Or they can even add new pipeline registers to break up one long, difficult journey into two shorter, easier ones.
Which really leaves us with a fascinating thought to end on. As we're designing chips with not just billions, but trillions of components, where does this powerful, incredible automation end, and where does pure human ingenuity and experience begin? Because right now it's clear that you absolutely need both. The tools can build a city, but it often takes a skilled human engineer to turn it into a true masterpiece.